So if you guys have a piecewise function, there's a couple things you guys need to remember about the piecewise functions. All right? First of all, we have three functions. Now, we should be able to graph all three of these functions. So if we graph, let's just graph y equals x minus 1 from algebra 1 that has a y-intercept at -1, goes up 1, over 1, or down 1 to the left 1. Good? OK. The next one is just the quadratic function. You guys remember that has that vertex at 0, 0, and it looks like that. And then the last one is a square root function, which is being shifted 1 unit to the right and then 1 unit up. So that graph looks like this. So all a piecewise function is, guys, is just a combination. It's just a combination of the functions. That's all it is. So, but the problem is, if we were to put all of these functions together, so this is y equals x squared. This is y equals square root of x minus 1 plus 1. So if I put all of these functions together, look how messy this is. Do you guys see how that function with all those functions together fails the vertical line test miserably? It's not a function anymore, right? So to make f of x a function, we have to restrict the domains. And we get the domain restrictions right here. These are the domain restrictions. So this says don't graph x minus 1 for all real numbers. Graph x minus 1 for only x values that are less than -1. Not equal to -1, just less than -1. So we look at our x-axis and we say, well, -1 is right here, right? So actually, if I was going down, so that'd be at -2. So that's right here. So I'm going to make a hole because it's not equal at -1. And I'm only going to graph values that are less when x is negative. Well, that's going to be all values to the left. That means everything to the right is not included in the piecewise function. Yes, it's a part of the graph, original graph, but that graph got restricted. Then we look at the quadratic function. And this quadratic function looks like this, but it says, I only want you to graph this from -1 to 1. Well, here's -1, and here's +1. Everything outside of that is not a part of the domain, right? It's a part of this function, but not this function that has a restriction. So guess what? We're going to eliminate all of this. And it's an open circle at 1 and a filled-in circle here. Then the next one is square root of x minus 1 plus 1, which is right here. But this says only graph this for values that are greater than 1. Well, fortunately for us, that's actually that graph right there. And is 1 included now? Yeah, so 1 is not included there, but it's included here. So guess what we have here now? We can fill that in. So now that is what the graph looks like. Looks pretty crazy. But if you really break it up, graph by graph, you can say, oh, OK, that kind of makes a little sense. Now let's go and take a look at identifying the domain and range from the graph. Because that's not just with piecewise function. That's with any function, any of those parent functions. If you know what the graph looks like, if you know the parent function and you know the transformations, you should be able to identify the domain and range. The domain is the set of all x values. Or otherwise said, how far to the left does the graph go, and how far to the right does it go, where it's defined. So we got to make sure we're looking for any undefined values. So you can see as far left to this graph, that as this graph continues, it's going to keep on going to the left, right? So the domain is going to be from -∞. And then we look, we say, all right, going to the right, is there any discontinuities? You say, yeah, there's a hole here. But at -1, it's not defined here, but is it defined there? Yeah, so -1 actually is a defined value of the function. It's just not for that function. It's for this one. And then as we continue, the rest of the graph is continuous. So the domain of this function, even though it has a jump discontinuity, it's still continuous with all x. Or sorry, it's defined for all x. We don't want to say continuous. Now let's go and look at the range. The range of any graph is basically saying how low does the graph go to how high is it going. And you can see this graph, as it continues in this arrow, it's going to keep on going down and down to -∞. And then as we go up, we can see the highest value here is -2. but -2 is not defined. So therefore, we're going to say -2 with infinity. Then there's nothing between -2 and 0. But then you can see there's this minimum value here. And then as that continues, now as this graph, the square root function, you should know that this graph is still increasing. It's just increasing very, very slowly. But as that graph draws, if I keep on drawing it all the way over to the end of the board, it's still going up. And it's going to continue going up for forever. So I just write union 0, because 0 is a defined value, to infinity. All right? Now, this is not a continuous graph, though. Right? You can't draw this graph without lifting up your finger or your pencil. So this is discontinuous. What is the type of discontinuity? Well, you're going from one function, and you're jumping to the next function. So this is a jump discontinuity. All right? And again, guys, we'll go through them. So let's review some of the other discontinuities. What other discontinuities could you have? You could have a hole, right? A hole discontinuity would be, what if I didn't have this as equal to? What if I had that as undefined? That means both of these values at 1 and 1 is open. Do you guys see see the difference between a hole and a jump? A jump, you're jumping from one function to the next, whereas the hole is just this value that's undefined on the graph. You guys see that? OK? And then the only other one we didn't talk about was a vertical asymptote. Well, again, guys, remember vertical asymptotes, when do those occur? When a function has values that are equal to 0 in the denominator. So let's look at each of these individual functions. Is that going to have a vertical asymptote? No. Does that have a vertical asymptote? No. Does that have a vertical asymptote? No. So our only options for discontinuities are going to be a jump and a hole. And also, you guys can also answer your question, is this function continuous? Before we restricted the domain, is this function a continuous function? Yes. Is this continuous? Yes. Is this continuous? Yes. So there's no other discontinuities. The only time we're going to have a discontinuities, if we do have one, is going to occur at what we call these breaking points. Right? And look at that. At -1, this is filled in again. At -1, do we have a discontinuity? Yes. At 1, do we have a discontinuity? No, because they're equal to each other. Now, how can we show this? Because what if you have something and you're on your test or your quiz or your exam and you're like, oh, crap, I can't graph this. It's too, I'm stressed out. I can't do this. How can we do this algebraically? So again, guys, we know that all three of these functions are continuous. So the only time we could have a discontinuity is where we go from one function to the next, which occurs at -1 and 1. So what we could do to test for continuity is we can just say, well, if this function is continuous, then don't you guys agree? Let's look at this one. X squared is equal to the square root of x minus 1 plus 1. This function is continuous. For the x coordinate 1, don't you guys agree that they have to have the same y value if it's continuous? Right? So what I'm going to do is I'm going to plug in 1 to show that they have the same value. It's continuous. You can see here, guys, at -1, they do not have the same y coordinate. So we'd say -1 minus 1 equals x squared. And therefore, this is negative. Oops, that's a -1. So therefore, this is -2 equals 1, which is not equal. And that's how algebraically you can show that is not continuous. And obviously, that also shows you that it's a jump, right? Because one y value is -2, and then you have to jump to the next y value, which is 1. The only time you would notice if it's a hole, because a hole would show that it's continuous, what you would have to notice is what we talked about. 1 is never defined. They both equal 1, but for both inequalities, it's not defined. Now, the last thing I just want to talk about here is, what about the value k? Did anybody write that down? No? That was on there. What if I said, well, what value k then makes the function continuous? Let's say I want to find the value k that makes this continuous. So then what we do is we do the exact same process. You would say, well, x minus k, if this is continuous, then these two functions have to be equal. Right? And they have to be equal at -1. So I just replace -1 for x. And then I solve. So I get -1 minus k equals 1, add 1, add 1. Negative k equals 2. K equals -2. K, not x. And guys, let's see if that makes sense. If k was -2, this would turn into x minus a -2, which is what? X plus 2. Look what happens. Oh, that doesn't. Is that at -2? This graph, this is a 1, minus 1. Did I make a mistake? X squared. That would bump that up to 2. That would not make that continuous. That's at 1. Huh? No. There's something. X minus k is equal to x squared. Oh, that'd be x plus 2. OK, yeah, that works. So that graph would be x plus 2, which would be over here, and then down 2, or down 1. So yeah, that would work. I was thinking of a different equation, yeah. So the equation's up here, but instead of it now being, yeah, you're not shifting the graph up 2. The new equation is y equals x plus 2, which is up there. So it would work. So you guys could see like that would now go from there. So yes, that would make that continuous. Anybody have any questions on the piecewise functions? Because that was basically a chapter lesson right there. Everything we covered. OK. Except for evaluating, right? That was actually the one thing I didn't mention. Sorry about that. Hold on. Remember, guys, I asked you guys to find the value of like f of 0. So let's look at this function. What is the value of 0? You guys can look at the graph and see the value of 0. What is the value of 0? 0. So why are you plugging 0 into all of 3 functions? It doesn't make any sense. You only plug in 0 for the function that has the domain that includes 0, which is the x squared. Right? So you just plug it into 0 squared. Don't plug it into all 3. And then if I said, what is the value of, let's say, 1? Well, 1 is not defined here, but 1 is defined for this function. Right? Or if you did -1. -1 is defined for this function, but not for that one. And you can see when you go to -1, it's defined here, which is 1. It's not defined for that function. So you wouldn't want to plug it into that function. Right? If you plug it into the first function where it's not defined, you would get -2. And you can see there's a hole there. It doesn't even make sense to give that as an answer. Right? So evaluate as well.